Problem-solving algorithms and heuristics. Newell and Simon's problem space approach, 1972, emphasized a reliance on general-purpose problem-solving algorithms and heuristics for the current purposes. An algorithm is a strategy that is guaranteed to find a solution. As an example, using a procedure to do long division in arithmetic is an algorithm. As long as you know the algorithm and the most basic arithmetic facts, you can generate the solution of any division problem. Other examples might be following a recipe exactly. As long as you follow the steps, you are guaranteed to produce the correct dish. A heuristic in problem solving differs from an algorithm in that it takes advantage of general knowledge to find a solution more quickly, whereas algorithms, if employed correctly, are guaranteed to find a solution. Heuristics may be faster, but are not always guaranteed to find a solution. A good heuristic usually results in the correct solution. Algorithms versus heuristics. As an example of the difference between algorithms and heuristics, imagine the scenario that we discussed in Chapter 1. You and your friends are planning to go out for the evening to a club, restaurant, or pub. You have been assigned to be the designated driver, which means you will not drink, and you have to pick everyone up and drop everyone off at the end of the evening. You wish to drive your car as few kilometers as possible. There are at least two possible ways to determine the shortest possible driving routes. One would be to enter everyone's address into Google Maps, enter your address into Google Maps, and enter the pub or pubs that you plan to attend into Google Maps. You could then construct a map that considers every possible combination until you arrive at the shortest possible one. In order to know which one was the shortest, you would need to calculate all the possible combinations. This is an algorithm, and although it would be computationally intensive, you would be guaranteed to find the shortest possible route. Alternatively, you could use what you know about the general geography of your neighborhood and where your friends live to estimate what you think would be the shortest possible route, perhaps starting with the closest friend and ending with a friend that is nearest to the destination. This is a heuristic because it is a cognitive shortcut that relies on general knowledge. It is likely that this would also arrive at the best possible solution, but it is not guaranteed. The trade-off is that it is computationally far less intensive. Given the trade-off, many people use heuristics to solve problems that are likely to result in the correct answer but require relatively less effort. Exhaustive search. The algorithm described above, which is considering all the possible alternatives, is referred to as an exhaustive search. The problem solver searches all the possible routes to the problem space and chooses the one that is the most efficient. This can be a workable algorithm if the problem space is sufficiently small and the problem is well defined. For example, suppose a young child is looking for their favorite toy, maybe a stuffed animal that they sleep with. The initial state is not having the toy that is needed for sleeping. The goal state is finding the toy. A given might be that this toy never leaves the bedroom. The problem space in this example is the bedroom, and the means for a solution are looking for the toy in the bedroom, looking under the bed, in the closet, under a pile of clothes, etc. Children looking for a lost toy in their room might employ the exhaustive search strategy. That is, they check everywhere. In the case of the lost toy, it would be a self-terminating, exhaustive search. The child would not search locations after they find the toy. This is a good algorithm for solving this problem because it is all but guaranteed to solve the problem. It can be generalized to other rooms, a hotel room for example, and if the problem is not solved, it would suggest that the toy is not in the room and therefore a bigger search is needed. But this algorithm becomes unwieldy when the problem space is larger. If the child needs to search every room in the house, or other rooms, cars, friends' rooms, the exhaustive search is still possible, but it will take longer and be less effective. In some cases, exhaustive searches are impossible. In chess, for example, there are 20 opening moves, then 400 moves from that, 7.5 million moves from that, and 225 million moves from that. Clearly, an exhaustive search is impossible for a human to carry out. People do not consider all the moves. They choose moves that are familiar, or a reaction to an opponent, or part of a style of play. Millions of other moves would never even be considered because they would make no sense. So an exhaustive search is not a reasonable way to play chess, and early chess programs that employ algorithms like this do not perform as well as good human chess players. 1985. Hill climbing. As noted above, an exhaustive search is ineffective with a large search space. One way to constrain the search space is to adopt a general-purpose heuristic like hill climbing. The hill climbing heuristic assumes that the problem solver only searches for steps that move the current state closer to the goal state. Computationally, this can be achieved by comparing the current state to the goal state and making some form of similarity calculation. See Chapter 2 for extensive coverage of similarity. The problem solver considers only taking another step if that step reduces the distance or increases the similarity between the current state and the goal state. Future moves are constrained by previous moves because each move cuts off other possible solution paths, like walking down a real path. You can only take a branching path that lies ahead of you. You can't take a branching path you have already passed. Thus, the problem space is constrained and the number of alternatives is reduced. Consider the example of literally climbing a hill. Suppose you are building a robot that will explore another planet or an inhospitable environment. One thing the robot needs to do is to be up to climbing to the top of a hill. The simplest way to achieve this is to execute commands that ask the robot to check the current altitude and only commit to another step if the altitude increases. In this way, the robot will continue to climb until no step will increase the altitude. The robot will be at the top of the hill. The only possible steps being evaluated at any given moment are those that advance the robot, and the step that is taken is the one that increases or advances the robot towards the desired goal. This reduces the problem space by eliminating any steps that retreat from the top. Of course, as you read this, you probably realize a serious limitation with hill climbing. If the hill is uneven, as shown in Figure 10.3, it is entirely possible that the robot can find itself at the top of a smaller peak that is below the main peak. In other words, the robot finds itself unable to take a step that will increase its altitude despite not being at the top of the hill. If equipped with only a hill climbing heuristic to find the top of the hill, the robot shown in Figure 10.3 will be unable to make it to the true peak and instead will settle on a local maximum. Figure 10.3. Hill climbing can be a useful problem-solving heuristic, but often results in the problem of local maxima, as illustrated by this hill climbing robot that cannot reach the true peak. A hill climbing robot cannot advance beyond this local maximum. So you can see the robot is on a smaller peak and he can't go forward into the crevice to get to the higher peak because then he would be going downhill, so he's stuck there. Hill climbing as a general problem-solving strategy can also run into a similar problem. In cases where the solution to the problem requires first working towards the goal and then working away from the goal, this heuristic will fail to find a good solution. As an example, consider the well-known puzzle problem called the Tower of Hanoi, also known as the Tower problem. In the simplest version of this puzzle, the problem solver is presented with 3 discs of 3 different sizes stacked on one peg. The goal is to recreate the tower on another peg. Figure 10.4 shows an example. In this case, the initial state is as shown, with the tower built on one peg. The goal state is shown on the lower right, with the tower built on the rightmost peg. There are 2 given constraints in solving this problem. The first is that you can only move one disc at a time. The second is that you can never place a larger disk on top of a smaller disk. Figure 10.4 shows a series of intermediate steps. One of the intermediate steps shows either the smallest or the medium disk on the rightmost peg. This is the peg that will eventually contain the goal state tower. In order to continue with solving this problem, the smaller disks are first moved onto the goal peg and then moved off the goal peg in a subsequent stage in order to obey the constraints of the task and make room for the largest peg, which is the base of the tower. The step seems to move away from the goal state. A strictly defined hill climbing heuristic would have difficulty with this move because it requires moving away from the goal state. As such, hill climbing must be supplemented or replaced with another strategy. Figure 10.4, the classic Tower of Hanoi problem, is a simple example of a problem that benefits from means-end analysis or the propensity to form sub-goals. Tower of Hanoi. Okay, we have a diagram now. So the initial state, you got like the three disks, and they're forming a triangle. The smallest on the top, then the medium, then the biggest on the bottom, and there's three pegs from left to right, and you're on the left peg. B, intermediate state. So now you've moved the smallest disk all the way to the far right peg, the medium disk to the middle peg, and then the largest disk is still on the left peg. C, intermediate state. You now take the smallest disk and you put it in the middle peg on top of the medium-sized disk, and then the large disk is still on the far left. The smallest disk must be moved back from the goal peg in order to solve the problem. And then D, in the goal state, now you can move the largest disk from the far left all the way to the empty peg on the far right, and then you can take the two disks from the middle peg and plop them on top, and then you have the triangle again. Means-end analysis. The simple example with the Tower of Hanoi suggests the need for an alternative way to reduce the problem space. One common way in which human problem solvers reduce the problem space even further is by breaking the problem into smaller bits and considering only one small part of the problem at a time. Newell and Simon refer to this as means-end analysis. In means-end analysis, the problem solver breaks an ill-defined problem into several smaller well-defined problems. With the Tower of Hanoi example, the entire problem involves moving a tower of disks from one peg to another peg. But this large goal can be broken up into many smaller sub-goals. For example, one sub-goal requires laying the foundation on the rightmost peg with the largest disk. This sub-goal can be broken up into smaller sub-goals still. In order to lay the foundation, it is first necessary to solve two additional sub-goals. The problem solver needs to make sure the rightmost disk is clear, and the problem solver needs to make sure that the largest disk has no smaller disk on top of it. By breaking the large problem up into several smaller problems, the solution can be attained by attending to and solving these smaller, more tractable problems. The same idea applies to cooking and meal preparation. When most people are preparing a meal, they often break the large goal of the completed dish into many smaller sub-goals. For example, collecting the ingredients, chopping and cutting them, and then placing the ingredients into small piles or bowls. The technical term for this is mise en place, which means literally putting in place. Creating the sub-goals makes the problem easier to solve and the meal easier to prepare. Means-end problem solving plays a role in the classic hobbits and orcs problem. Essentially, the problem is an expanded version of the Tower of Hanoi problem. It involves moving things from one area to another area with a set of constraints. The problem is stated below. 3 hobbits and 3 orcs arrive at a riverbank, and they all wish to cross onto the other side. Fortunately, there is a boat, but unfortunately, the boat can only hold 2 creatures at one time. Also, there is another problem. Orcs are vicious creatures, and whenever there are more orcs than hobbits on one side of the river, the orcs will immediately attack the hobbits and eat them up. Consequently, You should be certain that you never leave more orcs than hobbits on any riverbank. Note that the orcs, though vicious, can be trusted to bring the boat back from across the river. How should the problem of ferrying everyone across the river be solved? First, ignore the most reasonable solution that would satisfy our understanding of hobbits and orcs in the Tolkien sense, that is, get the hobbits across the river and leave the orcs on the other side. Figure 10.5 shows one possible series of steps to solve the problem. One challenging aspect for most problem solvers is that when all of the orcs are taken to the other side, it becomes necessary to bring them back again in order to keep the appropriate balance. In other words, at step 4, it seems as if the problem is half solved. All of the orcs are on the right side of the river. From here, the solver has to work backwards partially to bring the orcs back over the river. This can be difficult for a straight hill climbing heuristic. Means and analysis can break the problem up into smaller sub-goals. Early research with this problem confirmed that participants make more errors at these positions in the problem space. People make more errors and take longer to choose the next move when transitioning from the position shown in step 4 to the positions in steps 5 to 7. In other words, hill climbing as an absolute strategy will fail for the hobbits and orcs problem. In order to reach the goal state, the problem solver must break the problem into manageable sub-goals. In addition, research examining the ability of participants to solve problems of this kind suggests problem solvers require sufficient working memory resources in order to represent the problem variants, stages, and sub-goals. Figure 10.5, the hobbits and orcs problem cannot be solved via simple hill climbing. Step 1 shows the initial state. Step 1, all the hobbits and orcs on the same side, and the goal state. Step 12, all the hobbits and orcs at the other side. The intermediate means are steps 2 to 11, which show how the initial state is transformed into the goal. Problem solvers have difficulty at steps 4 to 7, when some of the orcs need to be moved away from the goal state. Working backwards. So far, we have been thinking of problem solving as a forward-driven series of cognitive steps. That is, we begin with an initial state and we move forward towards the goal state. Some problems, however, are better represented and solved in the opposite direction. This strategy is known as working backwards. For a very simple example, consider the kind of paper and pencil mazes that appear in coloring books and puzzle books for kids. There is usually a single way into the maze and a single way out. Solving the problem means finding the shortest path, and usually the only path, through the maze to the end point. In many cases, it is more effective to work backwards from the end state. Trying to solve the problem from one direction can only lead to false paths. As another example, consider the problem posed by Sternberg and Davidson, 1982. Water lilies on the lake will double every 24 hours. From the day the first lily appears until the lake is entirely covered, it takes 60 days. When is the lake half covered? This problem is pretty easy to solve, but it would be impossible to solve if working from a forward direction. We have no idea how large the lake is, and we have no idea how many lilies it will take to fill the lake. However, if we start at the end, when the lake is completely covered, and work backwards, it is fairly simple. If they double every 24 hours, then the lake will be half covered on the 59th day. From day 59 to 60, the half-covered lake doubles it to a fully covered lake. This problem is also an example of an insight problem. Insight problems are often accompanied by a sudden flash of insight or illumination. I will have more to say about insight later in this chapter. So the question is, when is the lake half covered? And you know it's entirely covered in 60 days. So then you know because it's doubling on the 59th day, the lake is half covered. The importance of problem representation. Many of the examples presented above emphasize heuristics and problem-solving strategies. Another way to think about problem solving is to consider how the problem is represented. In many cases, when people solve problems, they construct a mental representation of the problem space. Many of the strategies I have discussed operate on this representation. As such, it is crucial to represent the problem correctly. Earlier in this chapter, this was discussed in the context of Posner's bird and train puzzle. In that case, one representation made the problem difficult or impossible to solve, but an alternative representation made the problem very simple and trivially easy to solve. In this section, I want to examine the role of problem representation in greater depth. Choosing an appropriate representation. In Posner's bird and train example, the two representations were quite similar. The only difference is that one focused on the bird and the other focused on the train. Other problems require a more substantial change in representation. Consider this problem, which was first posed by Dunker. 1926. A monk leaves the monastery at 6 a.m. and gets to the mountaintop by 4 p.m. The next day he leaves the mountaintop at 6 a.m. and gets back home at 4 p.m. He travels at a very irregular pace and stops often. Is there a time when he is exactly at the same spot at the same time on day 1 as on day 2? On the surface, this problem appears to be impossible to solve. First, the representation is very sparse, and it emphasizes the irregularity of the monk's travel. We know that the monk starts and stops at the same time each day, but otherwise we don't know anything about the path that the monk takes. Second, the question itself focuses attention on exact times. The problem solver in this case may be tempted to solve the problem for exactly when and where the monk is on day 1 and day 2. Approached in this way, the problem cannot be solved. However, if approached in a different way, the problem is trivially easy. The simplest way to solve the problem is to represent it graphically. Figure 10.6 shows the hypothetical travel of the monk on the mountain. The y-axis shows altitude on the mountain, and the x-axis shows the time of day. On day 1, the monk ascends to the top. He starts at 6 a.m., and he ends at 4 p.m. at the top of the mountain. We can show this with an ascending line, and any line will work. I have drawn the line irregularly to emphasize that the pace was irregular, but this is hypothetical. We do not know the actual time, altitude, ascent rate. The second line starts at the top and descends to the base. It also begins at 6 a.m. and ends at 4 a.m. And, as you can see, the two lines intersect. In fact, it is impossible to draw this graph without the lines intersecting. Any two lines that satisfy the constraints of the starting and stopping time and location will have to intersect. In other words, framing it this way emphasizes that the question and problem are not about exactly where the monk is and when, but rather that there exists a time when he is in exactly the same spot at the same time of day on day 1 and day 2. This spot is where the lines intersect. It can occur anywhere along the trail and along the course of the day, but it must occur. Figure 10.6, a graphical representation of the monk problem. The y-axis represents the altitude traveled, and the x-axis represents the time of day. The circle shows the hypothetical intersection between time 1 and time 2 when the monk is in the same place at the same time on both days. Okay, the monk problem. So on the x-axis is time of day from 6 a.m. to 4 p.m. And on the y-axis is the altitude from the monastery at the bottom to the mountain at the top. So the two squiggly lines are day 1 and day 2. So day 1 moves from the bottom left at the monastery to the top right at the mountaintop. And on day 2, the monk begins at the mountaintop at the top left and moves down to the right to reach the monastery at the end of the day. And you can see that the lines cross. The intersection represents the location and time where the monk is at the same place and the same time on day 1 and day 2. Oh wow, that's really interesting. So there literally has to be a time and place where that is the case. Because the lines are basically like an X, like it's unavoidable. Now this doesn't of course solve like where that time is and where that place is, but the question doesn't specify that. The question just asks, is there a time when he is exactly at the same spot at the same time on day 1 as on day 2? So the answer is yes. Functional fixedness. Perhaps the most well-known example of problem representation is what is known as Dunker's candle box problem, or the functional fixedness problem, 1945. There are various versions of this problem, but the canonical version involves participants in two conditions who were presented with a series of objects and a problem to solve. The objects are shown in figure 10.7. Participants were given a candle, a box of tacks, and a book of matches. Participants were asked to use these objects to provide a way to mount the candle so that it would illuminate the room. In one condition, the tacks and matches were removed from the boxes and placed in piles on the table so that the participants saw empty boxes and the objects. In the functional fixedness condition, the matches were in their box and the tacks were in their box. The boxes were being used for their usual function, and so it was fixed. The correct solution, according to Dunker, is to tack one of the boxes to the wall and to tack the candle to the box. Thus, the box operates as an impromptu shelf. Figure 10.7. The functional fixedness problem, originally described by Carl Dunker, 1945. Participants were given the materials either as shown in panel A or as shown in panel B, and were asked to mount the candle to the wall so that it would illuminate the room. The candle box problem. Okay, so in the control condition, the matches and the tacks are outside of the box, and then you have a box and a candle. In the functional fixedness condition, the tacks are in the box, and everything else is the same. And the solution, of course, is to put the candle on the empty box. But if you start with a full box, it's harder to figure that out. In the initial study, most of the control subjects solved the task in the correct fashion. However, in the functional fixedness condition, fewer than half of the subjects were able to solve the problem correctly. Dunker's original explanation was that the function of the objects, namely the box, was fixed. When participants saw the box of tacks, they were far less likely to perceive the box as a potential shelf. Its function was fixed as being a receptacle for the tacks. One of the hallmarks of creative problem solving is to think outside the box and overcome the limitations of functional fixedness. 10.1. Theory in the real world. Dunker's original candle box problem has been studied and examined in many contexts. Most people are quite familiar with it now, and the solution probably may not even strike us as very novel. However, the idea of using objects for something other than their intended purpose to solve problems is something that crops up quite often in the phenomenon of life hacks. At the time when I was writing the first edition in 2014, and again in 2019 when writing the second edition, it was very common to see news stories, websites, and other media showing all the clever ways in which simple household objects can be used to solve novel problems. For example, using a dustpan to fill up a bucket from a sink, or using binder clips to organize the cords of your computer. Figure 10.8. An example of a life hack. The coin purse has been repurposed to keep headphones from being tangled. A rubber change purse can be used to keep headphone cords tangle-free. The photograph in figure 10.8 is one that I took of my daughter's repurposing of a simple rubber change purse to store her earbuds so that the cord did not get tangled. Most of us enjoy looking at examples of these novel problem-solving attempts for very clever life hacks. It is not uncommon to experience the sensation of satisfaction when seeing the example.